Welcome to our quantum deep dive. Today, we're diving into one of the most mind-bending concepts in all of physics, antimatter. We'll be exploring an essay by Jörg Oeschnebat to really get our heads around its strange and mysterious nature. Okay, let's get into it. So, let's kick things off with a pretty wild idea. This idea that every single particle of matter in the universe, you, me, the stars, has a mirror image. A counterpart that's almost identical, but with one critical difference, an opposite charge. Exactly. And this isn't science fiction, It's the very foundation of what we call antimatter. So let's really break down what that perfect mirror image actually means. And this slide lays it out so clearly. You take an electron, right? A fundamental piece of everything we know. Well, its antimatter twin is the positron. And as you can see, they have the exact same mass. The only difference is the charge. The electron is negative, the positron is positive. It's a perfect reflection, right down to the subatomic level. So, what happens when these mirror images, these perfect twins, finally meet? Well, it's not just a collision. They annihilate. They completely vanish, converting their entire mass into this incredible burst of pure energy. It is literally the most efficient and total conversion of mass to energy that we know of. And this is where the sheer power comes from. Einstein's famous equation, E equals mc squared, is the engine behind it all. The energy released is just immense because you're converting 100% of the mass of both particles. To put that in perspective, the energy from annihilating just 1 gram of antimatter with 1 gram of matter would be about the same as a large nuclear bomb. It's just staggering. But here's the wild part. Antimatter wasn't first discovered in some lab experiment. It actually started out as kind of a ghost in an equation. So let's look at how this mathematical quirk became a physical reality. It all kicks off in 1928. The physicist Paul Dirac is working on this big equation to describe the electron, but the math keeps spitting out two answers. One was for the electron we all know and love, but the other described a particle that just seemed impossible. But instead of just ignoring it, he made a bold prediction. It was a real undiscovered particle, a positively charged anti-electron. And then bam, just 4 years later, Carl Anderson is studying cosmic rays and he finds it. He sees this particle that acts exactly like an electron but curves the opposite way in a magnetic field, which proved it had a positive charge. Dirac was right. Antimatter wasn't just some mathematical ghost, it was real. Okay, so if antimatter is real, what can we actually do with it? Well, that incredibly powerful annihilation process has found a really remarkable and life-saving application in, of all places, medicine. It's used in what's called a PET scan. That stands for positron emission tomography. A patient gets injected with a special tracer that emits positrons, the antimatter version of electrons. This tracer is designed to gather in parts of the body that are really active, metabolically speaking, like tumors. Those positrons then meet up with electrons in the patient's body and boom, they annihilate. They release little bursts of gamma rays that a scanner can then detect to build this incredibly detailed 3D image. It's just an amazing example of taking the most fundamental physics and turning it into a tool that saves lives. But as this quote really hits on, working with antimatter is just incredibly difficult. Think about it. If it annihilates on contact with any regular matter, how do you even hold on to it? Right? You can't put it in a bottle. You can't even let it touch the air around it. You basically have to build the ultimate prison for it. At places like CERN, scientists use these super powerful magnetic and electric fields in devices called penning traps. And what they do is suspend antiprotons in a near-perfect vacuum. This whole environment has to be colder and emptier than deep space, all just to hold these tiny particles without letting them touch a single thing. And even with all that, they can only store them for a few minutes or hours before they're lost. It's an incredible challenge. And this difficulty, this volatility, leads us to probably the biggest mystery of them all. If matter and antimatter are perfect mirror images, then the Big Bang should have created them in equal amounts. But if that happened, they should have just annihilated each other completely, right? Leaving behind a universe filled with nothing but energy. So where is all the antimatter? And for that matter, why do we have a universe at all? And the answer, as far as we can tell, comes down to this tiny, almost insignificant imbalance right at the very beginning. For every 10 billion antimatter particles, there were 10 billion and 1 matter particles. After all the fireworks and annihilation was over, that 1 in a billion survivor, is what made up everything we see today. Every star, every planet, you and me, everything. This is what's known as the baryon asymmetry problem, and it's truly one of the biggest unanswered questions in physics. And trust us, scientists have looked everywhere. We've searched for entire anti-galaxies made of antimatter and found nothing. We've scanned the skies for the telltale gamma rays that would come from huge annihilations, and silence. It really seems like our observable universe is made exclusively of matter. So what could have possibly caused that initial imbalance? Well, one of the leading theories is that the mirror image, it isn't quite perfect after all. There might be a tiny crack in it, a subtle difference in the way matter and antimatter particles decay. This is a phenomenon we call CP violation. Now, here's the catch. While we have observed CP violation in experiments, the effect we've measured is just nowhere near strong enough to explain the enormous amount of matter that makes up our universe. So for now, the mystery remains. So to try and solve these deep mysteries, scientists are pushing the absolute boundaries of what's possible, and they're using antimatter itself as the ultimate probe to test the very laws of nature. And one of the biggest, most fundamental questions they're testing is this: does antimatter fall up or does it fall down? In other words, does it experience gravity the same way as matter, or could it maybe have some kind of anti-gravity? It's incredible. As you can see, experiments at CERN like AGIS, G-bar, and Alpha-G are designed to do something that sounds like science fiction. They literally create antihydrogen atoms and then drop them to see which way they fall. Now, our best theory, the standard model of particle physics, predicts it will fall down, just like Newton's apple. But what if it doesn't? If it falls up, or even if it just falls at a slightly different rate, it would completely upend physics as we know it. It would force us to rethink everything we thought we knew about gravity, about general relativity, and about the cosmos itself. It would be, without a doubt, one of the biggest scientific discoveries in a century. And looking even further into the future, the sheer energy density of annihilation sparks these amazing visionary ideas. We're talking about antimatter-powered spaceships for traveling between the stars. Or what about a totally new, incredibly powerful source of clean energy? Annihilation is thousands of times more efficient than nuclear fission. I mean, these are very distant dreams, of course, but they're absolutely rooted in real, solid physics. So, in the end, studying this strange mirror image of our world forces us to ask the deepest questions about our own origins. We exist because of a tiny flaw in the symmetry, a crack in the cosmic mirror. Understanding antimatter isn't just about a weird particle, it's about understanding why there is something in our universe rather than nothing at all. A huge thank you to Jörg Oschnepat, whose work formed the basis of this explainer. For more deep dives just like this one, you can visit schnepat.de. Thank you so much for joining us, and goodbye.
Schnepat.de is a private project by Jörg Oschnepat dedicated to promoting quantum technology. Its mission is to present knowledge in a way that is clear, precise, and transparent for those just starting out, as well as for experts who wish to deepen their expertise. He firmly believes that education and access to well-structured information are the keys to unlocking the full potential of this future technology. If his work helps you realize your own visions and actively and consciously shape quantum technology, then the goal of his project has been achieved.